Okay, so next we're going to be talking about motor control theories. So first we need to talk about what a theory is. So a theory is something that should satisfy two requirements. It must accurately describe a large class of observations, and it must make definite predictions about the results of future observations. So we need to talk about how theory connects to motor control. So suppose you need to help a person reacquire the capability to walk. Knowledge about the motor control mechanisms that underlie human locomotion and the environmental variables that affect it will allow you to develop more appropriate assessment and intervention strategies because they will be based on variables that influence locomotion. This is exactly what I do for a living. So when we talk about making theories, is that we have to be objective in the way that we intervene in someone who has a locomotion or a walking issue or any type of injury. So we have to be able to, understand and explain the theory that we're trying to use. We need to be able to figure out what that person or what level that person performs at. Do they have any limitations to what they can do? What's their potential to get better? So we're talking about kind of like prognosis. And then you or myself as the practitioner or the physiotherapist, you can start to identify what the problems are. You can develop a strategy to overcome performance problems. You can predict the effectiveness of your intervention strategies. You can develop systematic approaches to help the person increase skill performance capabilities. Then you can create new intervention strategies and then evaluate the effectiveness of those intervention strategies over time. So this is basically the realm of rehabilitation and an injury. So let's talk about some of the different theories. Let's talk about motor control theory. So the following sections discuss two essential issues important to a theory of motor control: the meaning of the term coordination as it applies to motor skill performance, and the degrees of freedom problem. So when we're talking about coordination, I guess think about motor control theory as what would be the things that we need to be able to use in order to have good motor control. Like in order to control our body, what are some of these components that we need? And so coordination is one of them, and then this degrees of freedom problem will be the other component of that theory. So in coordination, it's the patterning of head, body, and limb movements relative to the patterning of environmental objects and events. So let's just use soccer for example. We have to coordinate our head and body and limbs to the ball and the turf and the other players that are around us in order for us to perform the skill properly, or at least semi-properly. So this definition contains two parts. First, note that the definition specifies that coordination involves patterns of head, body, and/or limb movements. So we used to think of coordination as a characteristic of skilled performance, but it should not be limited to this use. When used in reference to a movement pattern associated with the performance of a skill, coordination refers to the organizational relationship of movement characteristics of the head, body, and limb involved in the performance, regardless of the skill level of the performer. So you don't necessarily have to be highly skilled to be coordinated, and that's a term that we hear in society a lot. It's just your scale of coordination, like how coordinated are you? It's basically it's a continuum. It's not necessarily you're coordinated or you're not coordinated. So don't necessarily think of, because you're highly coordinated, that you always have high skill related to the performer. The second part of the definition states that the pattern of head, limb, and body motion is relative to the pattern of environmental objects and events. This is important because it establishes the need to consider movement coordination in relation to the context in which the skill is performed. So I just talked about this relative to soccer. It's like you need to be able to move your head, body, and limbs in a way that matches the environment such as the ball or the turf or the people around you, so that you can interact with that sport or that skill in a way that is effective. Next, we're going to talk about the degrees of freedom problem. So, the degrees of freedom of any system reflect the number of independent components of the system and the number of ways each component can vary. This is basically saying, without me getting into too much detail with this other stuff, is you can interact with the environment or the system in a myriad of different ways. So there's multiple different ways that you can interact with that. So if we think of the elbow joint, it can vary and move in two ways, flexion and extension. So that would imply that we have 2 degrees of freedom. The degrees of freedom problem arises when a complex system needs to be organized to produce a specific result. So this control problem is as follows. How can an effective yet efficient control system be designed so that a complex system having many degrees of freedom is constrained to act in a particular way? So this is again a problem where if you have to think about what are all the different variables that are going into this skill, right? What are all the different ways that I can move? What are all the different factors that I have to think about? How many different ways can I move for this skill, right? So there's a degrees of freedom problem, that the more things that are moving, the more variables that are included, the more complex that it becomes, and that's where you have this degrees of freedom problem. Again, don't stress too much about this stuff. If you're lacking some understanding, there's other definitions that you can click on here. It will give you a glossary term here, and you can always search other things up and try and get a better understanding. They also do these a closer look components in this ebook. So if you need to read more about this degrees of freedom problem, there are other parts in here that you can get a better understanding of as well. I think there's a couple places where they do some good explanations about this as well. So if you feel like you're not understanding this degrees of freedom problem, you can read, I think this paragraph right here is a good understanding and a good way of looking at this degrees of freedom problem. Next, let's talk about open loop and closed loop control systems. So I'm going to try and explain this in the most simple way possible. Basically, an open loop system, you don't have time to react, or you don't get feedback relative to what's happening around you or relative to that skill. In a closed loop control system, you might have time to adjust, or you might get feedback relative to the movement or the skill that you're doing. So as you can see in the graphic here, you have your movement control center. You get instructions, like from your brain down to your spinal cord through your efferent neurons. You get this movement effector, like your muscle. You perform that skill. Okay, that's how it goes. You don't get any feedback, and you just keep moving on. And then the other way you will get feedback, you'll get this closed loop system associated with the skill or the movement. So these systems differ in 2 ways. The closed loop system involves feedback, whereas an open loop system does not. I just talked about that. In human movement, feedback is an afferent information sent by various sensory receptors to the control center, which is your brain, or your cerebellum, right? We talked about your error detection system. The purpose of this feedback is to update the control center about the correctness of the movement while it is in progress. The second important difference between open and closed loop systems relates to the movement instructions issued by the control center. In the open loop system, because feedback is not used in the ongoing movement, the instructions contain all the information necessary for the effectors to carry out the planned movement. Although feedback is produced and available, it is not used to control the ongoing movement. This may be so that because feedback is not needed, or because there's not enough time to use feedback effectively to control the movement after it is initiated. So let's look at some examples here. If you have an open loop system, you guys can maybe think of some examples on your own here, but a great example that I can think of right now is throwing a ball or hitting a golf ball. So when you throw that ball, once you release that ball from your hand, you don't have time to make changes to that throw. It just is what it is, and you will get feedback afterwards. You can't adjust your arm motion while you're making the throw. You are just making a throw, and then you'll see what happens afterwards. So that would be more of an open loop control system. Closed loop control system could be like walking in a crowded environment. You're always going to get feedback as to where you're walking. You know, am I bumping into people? Do I need to avoid more people? You're consistently getting feedback because that motion or that movement is continuous. It's kind of like always in the nature of I'm always consistently getting feedback from what I'm doing because I'm actively still doing it and I have time to correct things as people are coming. Like maybe you'll notice, okay, I got this person coming down the hallway. I need to get out of the way so I'm not getting hit by them. And that would be more of a closed loop control system. So again, look at a closer look. There'll be some other components in here. So like open loop, you know, digital video recorder or throwing a dart. You throw something, you don't get a chance to correct it. Closed loop control, you know, the thermostat in your house could be an example, but also like driving a car, right? You're actively doing that. You have time to kind of correct things. If you're kind of like veering outside of the lane, you're going to have an opportunity to switch that. This is kind of just another component that we talk about in the closed loop systems. I've kind of already talked about this to a degree, is, you know, the instructions can be a little bit different based on how much feedback you're going to receive. So it kind of just, again, using that cerebellum example from chapter 4, is just providing you with like some error detection and some smoothness to what you're doing in order for you to continue to respond to the things that are happening around you. And driving is a great example of that because it's allowing you to get consistent sensory feedback. Like you're kind of, again, visual feedback. Like, am I driving in the middle of the road? Right now, what are the vehicles around me doing? Like, what's the weather? What is the road like? Is it icy? Is it wet? Is it dry? You're consistently getting feedback as you do that skill. So there's a sensory component to that allows you to always adjust to what's going on around you. So let's talk about the two theories of motor control. So the first theory we're going to talk about is your motor program-based theory. So it's a memory-based construct that controls coordinated movement. So the first one we're going to talk about is Schmidt's GMP, or Generalized Motor Program. He used these things called invariant features that are the signature of the GMP, or Generalized Motor Program, and form the basis of what is stored in memory. These movement-related features form the basis of what Schmidt referred to as the fundamental pattern of class of actions. These features remain consistent from one performance action to another. So basically, the long story short is that invariant features stay the same from one action to the next. So let's say swinging of the leg when passing a soccer ball. And then he also talks about these parameters. So there's movement-specific parameters. These are movement-related features of the performances of an action that can be varied from one performance to another. So when you have your GMP, or Schmidt's GMP, if you think about kicking a soccer ball, well, swinging a leg is just consistent. You're always swinging a leg, but your parameters of how you swing that leg might change. Like you might swing the leg more if you're trying to kick it harder, or you might swing it in different directions depending on where you're trying to hit that ball. So that's a way that you can think about Schmidt's GMP. You have invariant features that don't change, stay consistent, and then you have parameters, or different ways that you modify those invariant features from one performance to the other. So again, how hard you move your leg, or how fast you move your leg, or how big you swing your leg, or what direction you swing it in. Those are parameters associated with this GMP. So, invariant features include relative time, so what percentage of the time is spent with each component of the skill. There is, a great example here using this graphic. So if we think of this is, kicking a ball, if you're doing this at normal speed, this might be the part where you bring your leg back. This might be the part where you bring your leg forward. This might be the actual kicking time, so how much your leg is going forward. And maybe this is the end of your follow through. So there are different ways of doing this, and different speeds in which you can do that. And so that's where they're talking about the relative time in your invariant features. So kicking is always going to take the same chunk of time for each component, but if you do it faster, it will still take the same percentage of time for that skill or that part of that skill, but it will just happen faster. So like if you move your leg really slowly, right, it would still take the same percentage of time to do each part of the skill, but if you do it a lot faster, it will just be a quicker movement with the same percentage of time spent on each skill or each component of the skill. So that would be the relative time component. So the parameters would be, like we showed up here, how much total time are you spending on that? I've said this example 400 times already in this video, but when you're kicking a ball, how much time are you spending doing that? Well, it depends on how fast your leg is moving. So that can vary from time to time, or like what direction you're moving it in. Those are all things that are relative time components when we're dealing with a particular skill. So that would be a parameter. So the second example of this could be like muscles. So when you change which direction that you move, you might use different muscles. So that could be a different parameter relative to the skill. So again, in the invariant variables or the invariant components are, what are you actually doing? You're just swinging your leg. But the parameters could be, how much total time are you spending, right? What muscles are you using? Those can be parameters as well. So the next part is Schmidt's schema theory. I don't really love Schmidt's schema theory. I don't mind his GMP theory, but the schema theory I find is kind of a bit confusing at times, and so I don't really worry about the schema theory too much, but we'll kind of talk about it in very layman's terms, I suppose. So if you think of your GMP, that's kind of your general movement pattern, just what we talked about. But your motor response schema is how that context affects the general movement pattern or the GMP, right? So if you are in different situations or different environment, how can you adapt to those different environments or situations? So, if the weather changes, if there's a crowd around you, are there components that you can adapt to by using the schema theory instead of using the GMP? So you can see I don't have a ton highlighted in that area because I don't really want you guys to worry about it too much. Next, we're going to talk about the dynamical systems theory. So in the dynamical systems theory, which is sometimes referred to as the dynamic pattern theory, or the coordination dynamics theory, or the ecological theory, or the action theory, just think of it as the dynamical systems theory. The basis for this theoretical viewpoint is the multidisciplinary perspective involving physics, biology, chemistry, and mathematics. Proponents of this theory see human movement control as complex systems that behave in ways similar to those of any complex biological or physical system. As a complex system, human motor control is seen from the perspective of nonlinear dynamics. This means that the behavioral changes over time do not follow a continuous linear progression, but make sudden abrupt changes. For example, in the physical world, when the temperature of water increases gradually, there's a specific temperature, 100 degrees Celsius, in which water boils and its behavior abruptly changes. This type of change represents a nonlinear behavior. So I basically wrote here that dynamical systems theory is basically a fancy way of saying there are many systems that influence the outcome of movements and that the movements are not influenced in a linear pattern. So I said we will be focusing on GMP and the motor control theories in this course to spend more time focusing on those instead of on the dynamical systems theory or the motor schema theory that Schmidt proposed. So you can see, not a lot highlighted here, so you guys won't see very much of this component on your quiz. In fact, I don't even know if there's a whole lot else left in this lecture. Here we go, right at the very bottom. So here's the present state of the control theory issue. So we now know, for example, that a theory of control cannot focus exclusively on the movement information that is specified by the central nervous system. We talked about this in the last chapter, right? When your motor goal or the action goal is different, then it's going to change the way that your brain and your central nervous system process that information. So that's why these theories can really vary, and people have different theories about them because it's not a definitive thing, right? It helps us kind of group together larger pieces of information, but it's not always 100% correct. And that's the thing about theories, is sometimes they get disproven and then we move on to a different one. So that is chapter 5. Please go back and review things if you feel like you need to. I know there's some components in here that are a little bit confusing because we're talking about theories specifically. I think if you think about some things that you want to kind of look at a bit more, you can think about Schmidt's generalized motor program. I actually put a link in here. You won't be able to copy it, but you can search Schmidt's generalized motor program, and there's a nice little video that is posted through YouTube or Google that actually covers this quite well. I think somebody did it for their project in a class similar to ours at a different school, and it's probably like 3 minutes long. And I would recommend that you guys go watch this component and this video on Schmidt's generalized motor program, because I think it'll give you guys a good understanding of what you're getting into, because this is something that you might be touching on in your final project. So please go back and review that, and the rest of the stuff later on in the chapter you don't really need to worry about for your quiz. And then we will see you for chapter 6.